Hi, my name is Shaun Smith, and I lead product management for GraalVM at Oracle. And today we're going to talk about optimizing applications for the cloud with GraalVM. So just for some context, there's a lot of activity at Oracle around Java. In particular, the two at the top are maybe the most well-known of the ones that I want to point out, which is OpenJDK project, which is an open source project where the Java language and Java platform are developed and evolved. And the GraalVM project, which is again open source or open core project, where we work on compiler technology. So we're specifically focused on finding ways to make Java run faster, more efficiently, and also bringing compiler technologies to enable us to run non-Java or non-JVM native languages on the JVM. So it's a fairly interesting project, but we're focused on compiler. So and that means speed. And this is what we're going to talk about today, is really how can we bring the benefits of GraalVM to your Java applications to run them better in the cloud. So GraalVM does have a number of different pieces involved. We have this same compiler technology we apply to a number of different areas, and I kind of touched on that a second ago, right? So we have a JIT compiler that plugs into the Oracle JDK. And so we simply swap out the built-in C2, the default C2 compiler, with the Graal compiler, the Graal JIT compiler, to accelerate performance of applications. Basically, this compiler produces more optimized code. So we do a lot more very aggressive inlining. We do a lot more interesting optimizations. We do a lot of interesting optimizations around memory usage. So we can avoid allocating a lot of memory, which helps reduce load on the garbage collector and so on. We also have this ahead of time compiler. So we compile Java bytecodes ahead of time at build time into native machine code. So normally when you're using the JIT compiler, that's happening on the fly when you're in your application. With GraalVM Native Image, that feature, we do this at build time. And there's some really interesting features in there, and that's what we're going to focus on. And the third thing we're not going to focus on today is that the ability to run other languages on the JVM. So GraalVM technology, or compiler technology, is pretty interesting. Has broad application. We're going to focus, like I say, on the microservices and container sort of use case today. So the goal for your cloud native applications, there's a few goals, right? You want your applications to start fast. And the reason you want to start fast is because in a lot of cases, especially a serverless scenario, you have to respond to a request quickly, and sometimes you're starting on cold machines. So you don't have an application running. You have to start that application up, respond to a request, and then reply as soon as possible. If you have to spend a lot of time booting the application, well, then you're just wasting time, right? You're introducing latency, and you're actually also introducing cost. Second is resource consumption. We want to keep it low. So you do want to keep your applications with lowest memory and lowest CPU possible. Again, because in the cloud, you're typically paying for those resources on a pay-as-you-go basis. So the more memory you use, the more you're going to pay. The longer you run, the more CPU you use, the more you're going to pay. So keeping the cost down is critically important. Now, you also want to have, if you're going to containerize your application, if you're going to containerize them for like serverless or Kubernetes, you want small container images. A couple of reasons. The most obvious one is small containers can be moved fast around the network. So if you're starting up, again, serverless is a good example, right? You make a serverless function call, and you're hitting a piece of hardware or a compute node that's naked, hasn't gotten any, doesn't have the container image for your function, has to pull that container image, right? Or even on Kubernetes, you start up a new pod, you got to pull that container image across to the machine you're running on. So transfer is important. It's also kind of related to the minimize vulnerability goal, which is you want to minimize, obviously, your vulnerabilities. So attack surface area, any kind of code, obviously a lot of Java code libraries are going to have CVEs. Some of them are not very important, not very serious. Some of them are more important and more serious. The less you can deploy in your application, the better. And that, we'll see how that's addressed in a couple of ways. One of them is picking a base image that's so a bit more hardened. And the second is by using GraalVM Native Image to remove parts of your application you're not actually using to reduce the attack surface area of your application. So got a lot of interesting goals here. We'll dig into them. So a little bit more as we get started on GraalVM Native Image. So I mentioned it's an ahead of time compiler. It takes your jar files, your class files containing Java bytecodes, and transforms them into a standalone executable, right, for a Linux, Windows, or a Mac OS. And it does this in one go through a process where we walk through your application, looking for all the code that's involved in your application to service the code you're writing. Now, before I sort of delve into a little bit more detail, let me just give you sort of examples of what this means, because these applications start really fast and they consume a lot fewer resources just by being compiled ahead of time. Let me give you a concrete example of that. So the Spring team, they've been working on a project called Spring Native. It's kind of an experimental incubation project as they work towards Spring Boot 3, which is coming out in fall 2022. So Spring Boot 3 is going to have this functionality incorporated, but the work they were doing in the Spring Native project was really interesting. They took the Pet Clinic, the sort of well-known Spring Pet Clinic application, and they compiled it with native GraalVM Native Image. And you can see the results here. On the memory, you've gone from 417 megabytes for RSS, for the memory your application needs, to a mere 101 megabytes. So basically, they shaved 75% of the memory cost off of this application. Startup time went from 2.6 seconds to 158 milliseconds, which is a 94% savings on memory. On startup time. The thing starts basically instantaneously. And we'll discuss why that is. The build time went up significantly. And in this case, this is an early result, and it's much better now. And there's a number of different features we've added since this data was gathered. But build time is slower because you're not amortizing the cost of your native machine code generation to runtime. You're doing it all up front. So there's a bit of a cost there up front. Works fine if you're in a CI/CD system. You don't really notice it. On your desktop, we've got some features to do quick builds to improve the developer experience of working with native image. The reason GraalVM Native Image is catching on or is getting so much attention is because of the wide adoption we're seeing in microservice frameworks. So amongst the most well-known, Micronaut, Helidon, Quarkus, and Spring. Of course, there's Tomcat has embedded Tomcat, which is working with GraalVM Native Image, and Netty. And each of these frameworks, particularly obviously the top four, they're designed to give you some guardrails to keep you on the straight and narrow. So working with the GraalVM Native Image, Java was not designed to be compiled ahead of time. And so there's some features of the language which are difficult to deal with, or at least require extra configuration. So for example, if you're using reflection, you need to declare to the GraalVM Native Image compiler or utility that your certain methods need to be included in your application, because static analysis that we perform will not find this reflective use. So these frameworks are designed to help you build applications that are going to compile and run successfully. So they're highly recommended if you want to succeed with GraalVM Native Image and ahead of time compilation. Getting a framework that's compatible, designed to work with native image, is actually recommended. Now, in terms of the sort of comparisons between the JVM and GraalVM Native Image standalone executables, it's pretty significant. So we saw on the Spring results how fast it had booted. So you see here on the left the same kind of thing. We've got a simple Hello World application just to compare it against other languages, and not just the JVM. Because a lot of people, as they move to cloud, are asking the question, do I need to learn Go, right? Do I need to change from Java to something else? And I really don't believe you do. So you look here, the performance or profile in terms of boot up and execution time of a native image application. It's pretty much in between C and Go. It's quite good. There's garbage collection going on, just like in Go. There's some overhead that's going to be you're not going to see in a C program, but the benefits are worthwhile. And compared to the JVM, it's a lot faster, and I'll explain in 1 second why it's so much faster to start. But that scale is logarithmic, so it's quite a lot faster than the JVM in terms of boot. And we saw that in the Spring numbers, right? 94% faster to start. And then in memory usage, we have a lot less memory being consumed too, right? Again, we're back down in the C-Go space for memory. This is not logarithmic scale, it's regular linear scale. A native image application consumes a lot less. And again, there's some reasons that I'll explain to you in the next slide. But really, back to the point about the goals, right? Faster startup, lower memory consumption, reduces your cloud costs for sure. Okay, so here's a couple of charts that kind of explain a little bit about, or maybe provide a way for us to understand what's going on at runtime with these applications. So on the left, I've got the same application here running. It's a simple hello world type application, web service. You ping it on a port, on a HTTP socket, and you get back hello, right? And we basically boot this application, and then we talk to it once every second. We just basically ping it. On the left, you've got just-in-time compiler on the JVM, right, in typical JIT mode. And all that red is CPU. So when you boot an application on the JVM, you give it an entry point, and the JVM loads your classes, right? Starts loading classes, starts loading bytecodes. Those bytecodes have to be parsed. Some internal structures are built. You go into the interpreter first loop, at least, and then your code will be compiled by the C1 compiler. And then there's some analysis performed to determine where in your code it's hot. So, hotspot compiler, right? What code is important to optimize further, and you get C2 compiling the code again, and basically really optimizing the code as much as possible. And all that takes CPU, right? So you got a lot of parsing, a lot of processing. You've got a lot of things going on, and you see the blue memory line there. The memory is showing you there's quite a significant rise in memory consumption until it kind of levels off. And that memory consumption is, again, pretty much because of the overhead of the JIT compilation. So JIT compilers have to keep profile data so they know what code to optimize. They have to keep code caches around. They have to keep bytecode caches around. So you got native machine code, you got the bytecode, you got profile data, you got all kinds of things happening that are adding footprint to your application. And then you see after it settles down, all that sort of initialization is done and a lot of CPU is done. I think that it's a small apps, the code's hot, and then you see these little, just at 4 and 5 and 6 seconds, you see these little flicks of CPU. On the right-hand side, you see what it looks like when a GraalVM native image or a native executable boots up. Not a lot of CPU at the beginning. You see a little bit more at the beginning than you see later. Later you see a little bit, and these are small little blips there later on as the processes or the requests are made. But what happens when you boot a native executable is there's still garbage collectors to start up. There's still some overhead to initialize. Of course, you got to read config files or whatever you've included. But you've got machine code, right? You just have machine code. You don't have bytecodes. You don't have any profiling data to worry about. I mean, you jump right into machine code. So you just jump into it like you would a C or Go program, right? You're just right into machine code. So all that initialization is gone, and then all the memory overhead for all of that sort of compilation infrastructure is eliminated. So the memory consumption, again, is low. And you're really going to pay for the memory your application uses, right? You really can't get away from, if your program allocates an object, it allocates an object. So you'll pay either way to carry the cost of that object. But you don't have to carry the cost of the full JIT infrastructure in a native executable. So the advantages of GraalVM Native Image or GraalVM Enterprise Native Image, and that's the commercial version of GraalVM, is over the open source community edition. So we do have an open core model. We build in GraalVM in open source at the graalvm.org project. But we have the GraalVM Enterprise and a significant number of advantages. So the first is that there's more additional compiler optimization. So in benchmarks, you'll see that the GraalVM native image applications GraalVM Enterprise applications are significantly faster. So there's more optimizations, more advanced optimizations included in those applications. The second is we include a feature called profile guided optimization. And this is something you might see in a typical C program. You run your application with some monitoring turned on. You gather metrics about your application performance, and then you recompile the application with the performance data. This is not dissimilar to what the JVM does with its constant profiling of data, right? But it's constant ongoing. We can do this one time, or we run this in your environment, gather some metrics, recompile, and then you've got an optimized application tuned for your use case. The GraalVM Enterprise native executables also include the G1 garbage collector. So it's much lower latency garbage collector, so improved performance, and includes some compressed pointer support, which means that we can squeeze a smaller heap application into a much smaller space, right? We can compress the pointers and keep your memory footprint low. So really focus on keeping it small, keeping it fast, right? That's the main goal. Now, the great news is that GraalVM Enterprise is free to use on OCI. So if you're deploying on OCI to serverless functions, you're deploying to Kubernetes, or you're running on a virtual machine, GraalVM Enterprise is free to use, fully supported. You'll see all the patches appear on a regular basis, and you can, if you're on Linux, you can yum install the code. It's all there for free. So it's at no additional cost. So really this helps improve the value proposition, sort of the OCI platform, which is already a very competitively priced platform, where you can also, using GraalVM Enterprise, improve the performance of your application. So again, you get a bit more for your money. So it's a nice feature. Okay, so I've told you a little bit about it, what it's doing, or some of the qualities, and like how does it work. It's fairly straightforward. I mean, at a high level, it's straightforward. At the details, it's a bit hairy. But taking your application, let's say it's a hello world, right? And we'll look at a hello world example in a second to see how it runs. You have a main function. That main method will refer to other classes and so on and so forth. So what we do is take all your inputs and we start walking statically. We use a static analysis to walk through your code from the point of entry to all the places you can reach, all the classes you can get to. You may have some initializations you have to run. So some initializations need to run at build time, some at runtime. You may need to run some of those initializations may create some objects. Those objects or those classes are referred to, point to other classes and so on. So we keep going around the circle until we get all the classes you need. In fact, we do a very precise analysis. So we look at the classes you need to include in your application. We look at the fields of those classes, because some fields may not be necessary. And we look at the methods of all the classes you use in your application. And we only take those classes, methods, fields that you actually need in your application and generate a machine code for those classes. So we actually don't, you'll have classes in your machine code version of your application where fields are removed because you don't need them. Methods are removed because you never use them, and classes you never refer to that come from the JDK or from third-party libraries you're using, they're also removed. So you just get what you need, We also write up the heap. So I mentioned initialization. So if you're running some static initializers that create objects, those objects have to be snapshotted and written into the heap. So those go into your executable too. So the output of the analysis is a binary for the architecture that you're working with. Now, I mentioned performance differences. There's a significant performance difference between GraalVM Enterprise and GraalVM Community Edition, but even within GraalVM Enterprise, there's some options that affect the performance. So in particular, the profile guided optimization and the G1 garbage collector. So on the far right side, you see the JVM. We take that as a baseline. So if we have a large test suite. You can imagine as compiler engineers, our team is focused on large amounts of benchmarking. We have a large benchmark suite. This one here includes Renaissance, Da Capo, Scalabench, numbers of different benchmarks on 17. We ran all those and called the performance on the JVM the baseline benchmark, like one. It's one, right? If you start on the far left here, GraalVM Native Image, the Enterprise Edition, the throughput is actually about 70%. So with no intervention, the application will run a bit slower, right? Because the hotspot application is able to learn about the performance of your application and tune that application for your use case. So out of the box with no information, today, GraalVM Native Image will run a bit slower than the JVM. If you then bring into play profile guided optimization and the use of the G1 garbage collector, we can see that the performance in this case on all the benchmarks we're on right now for JDK 17 as of today, we're running a little bit faster. So it kind of goes to show that ahead of time compilation does not have to be slower. Out of the box, it might be if you don't do the necessary work, but you can actually get those applications tuned to even outperform the JIT compiler, which is a really interesting result. And it certainly wasn't the case in the past. So GraalVM has achieved these benchmarks in the last year. The second thing is memory reduction, comparison of memory reduction. So the JVM, again, same thing. We took the JVM as a benchmark of 1. And then we compared the same memory consumption of the same applications, the same benchmarks, running either as native executable on the far left or with native image with PGO and G1 enabled. And what we found was that out of the box, native executables are really efficient, right? So we can shave off like 54% of the memory right away in all those benchmark suites. So it's a relatively consistent result on a large suite. We save quite a bit. If you turn on in the center graph here shows you with PGO and G1, it's a bit bigger. So particular G1 adds a bit of memory footprint to the application, but it's sort of the classic trade-off between space and speed, right? So you can go faster with when you use PGO and G1, but you're going to have a little bit more of a memory footprint to do so. So really it's up to you how you want to tune your application. Are you optimizing for memory? Are Are you optimizing performance? Or are you looking for a balance between the two? Well, I think we should see some code. So here's what we're going to look at. So this is hello world, right? So let's just look what does it hello world look like if you compile to native executable? And this is the question we want to answer. So let me slide over into VS Code here. And I've got a few things set up here. So I've got a demo with here's the application, right? So hello world. What I'm going to do is I'm going to compile that with, well, I'm going to run, first I'm going to Java C. I'm going to compile it with Java C. So Java C, hello, oh, I'm in the wrong place here. CD into demo. All right, that's better. Oop. Clear, and let us focus here. Okay, so let's go Java C, hello.java, right? The application we're looking at there. And of course that runs really fast because really Java C is really just translating it's doing obviously a lot of checking, but it's translating your source code into bytecodes. Still very high level, not machine code, obviously. I can run it, right? Java, hello, runs great, right? Now let's compile that into a native executable. So we'll run native image. And this is the utility that you can run as part of the GraalVM distribution. This is a really simple case. This is really, there are many command line arguments one could use. I'll just pop this bigger. This will work fine for a single class. So a lot of analysis goes on. You can see here the analysis, how many classes are reachable, how many fields are reachable. Oh, okay, it's done. It's pretty quick. It's a very small application. But you can see here we're going through and doing a full analysis of reachability. Then we go through and have to generate code and so on and so forth, build the image. There's a few statistics interesting. Where are the classes coming from in your application? What kind of objects do you have mostly in your application, in your heap that we're snapshotting? And you see here we use about 3.4 gigabytes, CPU a lot too heavy. So the nice thing is that the GraalVM Native Image utility can run in relatively small-ish environments. Again, this is in the last year, I'd say a huge improvement in the performance of GraalVM Native Image utility. It makes it work nicely now in GitHub Actions and in the OCI DevOps service. Anyway, it's generated this little binary, hello. I'm going to LDD that hello, just show you that this thing is a binary, and these are all the shared libraries that are linked to that executable. So I can run it. Does the same thing as the Java application, right? It's not very exciting. If I take a look at how big it is, oh, let's do it. I just like the H for human readable is always good. 6 meg, right? So it's a 6 meg standalone program, shared libraries or additional runtime. But what's interesting about this is really the speed, right, that this thing boots at. So if I run, if I time Java hello, so I'll run JVM boot hello, and this is a really small application, right? That boots pretty fast. So 55 milliseconds, 55, yeah. Okay, so there's a bit of caching going on. But you can see the kind of time frames we're talking about, right? In terms of real time, we're in there. If I do the same thing, if I run time and I run my hello world here, it's 2 milliseconds, right? 2. So again, we're seeing this is again around 4%. You're shaving off in like 96%, 94% of the boot time. So this boots really fast. So if you're building command line applications, GraalVM Native Image works great also, right? Because you've got this little easy way to build CLIs that are extremely responsive. There's no lag while the user types a command. It just responds instantaneously or relatively instantaneously. So that's interesting. Let's see what this really means, though. I mean, that hello world's fine. Let me go over to another example here. I got a small Micronaut application. It doesn't do much either, but it does boot up an application. This is the Micronaut sort of main program, boot the application. And I've got a controller which is listening it's a HTTP service listening on hello. I've pre-compiled this actually, so let me just go over there. Because it takes about a minute to compile this application on this particular machine. And all right, I'm gonna go into the target. So using Maven here, I built it. So I got the service, I got the class, the executable, and I got a executable jar here. So let me just run this on Java, the jar. What's good about this is, if I just zoom this up here, What's nice about, oh, that did not work. Oh, let's just try this again here. I'll just pop out here and do a rebuild. We use Maven W, and we will say package. So you can see this is working. That's good. Great. Okay, good. Let's go back in there again. And we do Maven W, or we do Java minus jar. Maybe I should just get this right. Java minus jar, the hello service. All right, there you go. So it boots up, right? So you can see here, it says 607 milliseconds listening on the port. Okay, so it basically doesn't do much. Let me try that again, just to run this one more time. Give it a try. 600 milliseconds. I'll do it one more time just for comparison. Okay, 624. So this is a typical small microservice application. It's booting up in over half a second. Okay, as a fat jar. Basically, run the JVM. I've got this application here, this hello service. It is itself 60 meg in this case, so it's a bit bigger. It has a number of more moving parts in it than the last time on the simple hello world. Let's try that. Let's run that one. I'm just going to type hello service. Okay, it boots up in 24 milliseconds. I'll try that again just to compare. 23. Oops. And one more time just for, okay, 24. So it's pretty consistent. Again, we're seeing that same kind of change. The reason I used this example was because Micronaut pleasantly tells us how long it takes to boot, which is really convenient. So it's kind of helpful to see the boot time because it tells us itself how long it takes to get basically up and running and listening on that port. So if you're building microservices with Micronaut, Spring, with Quarkus, and so on, you can see the attraction to using native executables for this compilation. And I'll move on a little bit, and we'll talk about what this means for containerization in a second. Let's go back over into the slides here. All right, so let's say I want to take this application and containerize it, right? So what does that look like? Well, if you look at a typical Java app, you've got the app code and its dependencies, right? So all your third-party jars. You've got JDK modules. You've got the hotspot VM itself, the runtime. And you've got some base OS image, right? This is your basic stack. This is what you've got to start with. This is I guess, the naive starting point, right? Just run my app. You say, yeah, run the JVM, fine, it'll work great, and it'll work. But what we can do first off is choose a better base image, right? So we want something slim, a slim base image, or even distroless. If you've seen Google Distroless, where they are building images that are minimal, contain the fewest possible libraries and components that you need to run your applications, and they remove the tools to actually install additional components. So basically, they're read-only, write-once container images. So that's one thing we can do. We can bring down the total size of our container we produce by just choosing smaller base images that are hopefully even more secure, right? In the case of distroless, they are slim, maybe not so more secure, but certainly a lot smaller. Second thing you can do is you can use JLink. So JLink is really the way you want to be building and distributing apps today with Java, if you're using the JVM. So we can use JLink to remove those modules from the JDK that you do not need. So we're just left with what's required in the JDK. So we're whittling our way down to less code, right? The problem is that JLink kind of doesn't know anything much about all your app and all your dependencies in a sense. It will only include the ones you need, but it either brings in a module or it doesn't, right? And that's the level of granularity. It's fairly granular. But this is not a bad start. Now, if we move to GraalVM Native Image, and I'm going to introduce this static option here, and I'll get around to static in a second. But if I'm using GraalVM Native Image, I can actually get rid of the needed code. And I mentioned before what we remove from your application, right? What we don't package. I can get rid of the code you don't need from your application that you think you've written yourself, but included in possibly even a company provided utility jar where you need one or two classes. We'll get rid of all the rest that you don't. And also, it'll get rid of JDK classes you don't need. So even beyond the module level, we can go sub-module, and we will remove all the classes, really all the classes you don't need. Just leave with the ones you do. So it's a little bit smaller again, right? And then What I really want to do is I want to put this into a really small container image. And the best way to do that is to statically link the application and put it into an image that contains almost nothing. So static linking, well, let me skip over here. If we statically link, what we're going to do is we're going to compile your application to a native executable, and then we're going to statically link in libc. So you get one application. You know when I typed LDD earlier to see which shared libraries the application had? If you deploy your application into just a typically compiled application into this has shared libraries into a container image, that container image has to have those shared libraries available. And it may or may not, right? It's an issue. It's something you have to manage, something you have to deal with. If you statically link it, it means that all the libraries you need, when you build it, get basically embedded into the binary, so you have one binary. And that means you can go in and deploy this on much more interesting, thinner container images. And the bottom level here, the hotspot VM is basically replaced in a native executable by a thing we call substrate VM. It's the thin layer of services. It starts the garbage collector. It provides all the services that the JVM provides to your application, but in a fairly thin, light manner. So what I'm going to do is I'm going to take this self-contained binary, right, at this point, and I'm going to put it into a Scratch image. So Scratch contains basically nothing, right? So you've got the kernel from the host OS, but your container image contains no operating system. It contains just your binary. And if you statically link your executables, include everything it needs, then you can pull this off, right? So really I can build a Scratch, like on the left here, I can build a Scratch, a Docker file that says from Scratch, copy in that application into my container, and then when you boot the container, boot the app. And that's all there is to it. So with Hello World, that Hello World we saw, I can certainly get to less than 6 megabytes. In fact, I can get even smaller on that Hello World. So let's go check that out in one more demo. All right, so I'm going to go over to a different place. So what I've done is I've actually grabbed something a little bit bigger. I've grabbed this JWeb server, and let me just change to a different build here. So JWeb server is a new thing, or a new feature came out in JDK 18. It's a Java. It's a web server written in Java that's in the JDK, and you can use it to just host up files. It just hosts files. And I said to myself, what's the smallest possible Java app I can get that doesn't bring in third-party libraries? And I realized the JWeb server does the trick. So what I'm going to do is give you an idea of the difference between static linking or how I can statically link and put it into different container images, and also use other tricks to further shrink my application down. So what I've got here is, let's see, I've got a build file. I'm going to run this build file. And what it's going to do is it's going to compile the module. Let that run for a second. Actually, while we do that, I'll go over and we'll look at the build. So I'm going to run native image. I'm going to say I want it statically linked. Everything's linked together. I'm going to link against the musl C library, which is a lightweight library that replaces glibc. I'm going to go to the module, which is the JDK HTTP server, and we're going to basically, that's my entry point, and there's a main class in there that is automatically picked up. And I want to compile that and output it into an executable called JWeb server static. Then what I'm going to do is I'm going to build the Docker image out of it. We'll take a look at that. Then I'm going to use UPX to basically compress that image. So I can use actual compression on the binary itself, because I have this one thing, right? It's not like I have a collection of jars and classes and hotspot. I've got a single executable. I'm going to use UPX to shrink that executable. I'm going to Dockerize that too. I'm going to containerize that same application. So let's see here. This doesn't fit too well. I'm going to go a bit. There we go. It's a bit better. So if you look here, we compiled the application. So this is the JWeb server. It's compiled down. So as an executable, it's 20 meg, which is nice small. I mean, compared to Micronaut, I mean, this doesn't do much, but it's pretty compact. So 20 meg, and I've got a binary that basically serves up files. When you boot this up, if it finds an index.html file in the current folder, it'll serve it up. Otherwise, it'll let you sort of wander around the file system looking at files and folders. And that same application, I've taken it and I've used UPX to compress it. So it's down to 5.2. So UPX will take the executable, compress it, and yet you can still run it, right? So for example, I can run at this point JWeb server UPX, and it starts up, right? So it basically automatically uncompresses itself and runs the application. That works great. If I take a look at the Docker files I've built here, they're rather boring Docker files, which is kind of the point. I've got from scratch, and if you know what I'm talking about here with scratch, there's nothing in there. I'm copying the application into the root. I'm copying the index file I want to share. And then I'm saying, when you start the Docker container, run the static server, the application, and give it some, like what port to listen on to and what folder to serve up. So it's really small. UPX is exactly the same. I'm just copying it in. What's interesting is if you take a look at the Docker files here that we build, same thing, right? So I've got the UPX tag, the UPX version of the Docker container image is only 5.4 meg. The static one is basically the same difference of the binary. So really, when you're copying a binary into a scratch container, you're not really adding much additional. Like the container image is pretty much the size of your application itself. So I've got these container images, and I can run these, right? So I can do a Docker run. I can do -p for the port. It's 8,000, isn't it? It likes 8,000. And it is JWeb server :UPX, for example, right? Starts up. There we go. It's listening on the port. I'll go into a different terminal, and I'll curl it localhost 8,000. Right, it serves up the file. That's the file I have there. It's hello world, right? So that's this index.html file. So it serves it up. So it works great, right? So what I've done here is I've taken a Java, like this is a Java application, it's a Java web server, and it's a 5.4 megabyte application. I think it's really, personally, I think it's quite astounding. But it gives you an idea of what you can do. So let's just go back over to the slides here and sort of review some of this content. So just so you understand the differences, we actually have three kind of linking options that help you customize what the application for the kind of deployments you want to have. So what you saw was a fully static, right? No libraries are provided by the OS. It's your code. So this gray box is your application. It contains libraries you need. It contains the C library you need. You can stick it into a scratch container. It's really small. You can go in the other way, which is when you saw me compile hello world and the Micronaut application earlier. The binary just contained application code, but it had shared libraries and it had libc, and they were all provided by the host environment. And if you go in like a slim container or just a standard Debian, Ubuntu image or a slim one, this will work pretty much out of the box, right? Because all these libraries, most of the libraries are there, and if not, you have to install them, right, using yum or APK, package manager. It's probably the biggest size of container you're going to get out. And then we have another version which is called mostly static, which links everything in except for libc. And there's a couple of reasons. One is libc being provided by the environment. If you're using glibc, which is the default one, glibc is not really designed to be statically linked. So for ease of distribution of your application, linking everything but glibc in this case means you can run in certain environments, like Google Distroless offers a version of their container images that contains pretty much nothing but glibc, or nothing additional but glibc, so it'll run. So it'll fit. So it's kind of medium size, right? So it's a little bit bigger because these application environments need to have a little bit more in them. So you have a lot of choices about how to customize your application, take full advantage of the containerization. And picking these nice, secure, small container images. So I'm going to sort of review here, but just I think we've covered all this ground. But we've gone through GraalVM Native Image. Starts fast. It reduces your resource consumption, right? Lower memory. We've seen that in a couple of cases. Those container images are small. We saw a container image for a full web server that was only 5.5 meg, which is kind of astounding. And you saw we were able to use container images like, well, at the most extreme, Scratch, and then from there we could use Distroless, we could use something else to minimize your vulnerabilities, right? Remove stuff you don't need, take out those attack vectors so your application is more secure. So in summary, GraalVM Enterprise JDK, which is the JVM, sort of harkening back to the first slide, talking about the JIT compiler, even running with the GraalVM JIT compiler will reduce your application memory and improve performance. So if you're not ready to go to native image and compile ahead of time, you're not doing microservices, the GraalVM Enterprise JDK does do the trick, right? It will help improve your performance and reduce your memory consumption. But if you're using GraalVM Enterprise Native Image, right, it's perfect for microservices and serverless functions across platforms. Things start really fast. We saw the performance is basically on large benchmark suites is competitive with JVM, so you're in the same ballpark. So you shouldn't see a performance suffering from performance by making this decision to compile ahead of time. But when in doing so, you reduce your memory requirements, you improve your application security, and as we've seen, all these popular is compatible with all these popular sort of container images. It's also supported, we saw, by all of these third-party or downstream microservices frameworks, right? So Micronaut, Quarkus, Helidon, Spring, all those guys are all designed to work with GraalVM Native Image, making it much easier for you to use. So you can learn a lot of details. You can just use those frameworks, and basically they'll help you along on the path. And in summary, it's all free on OCI. So if you're using GraalVM Enterprise on OCI, it's 100% free. Install it on any compute platform. You have access to the compute. You can install it. You can put in containers and deploy. And by doing so, you get access to regular service updates and security patches. Well, that's all I have today. Thanks very much for your attention. I hope you find this really interesting and give it a try. Go to oracle.com/GraalVM to download and try it out. Thanks very much.